Pulleys 2. This video covers a second example of a pulley problem and what happens when the heavier mass hits the floor. We'll get to it, but essentially when the heavier mass hits the floor, a string goes slack, so there's no longer any tension. If the forces acting on the masses change, then the acceleration of the masses change. Okay. As with example 1, it's sensible just to go through and draw out the situation as the first step. So a light, inextensible string passes over a smooth, fixed pulley. To one end a mass of 1.5 m is attached, and to the other a mass of 5 m. Once the picture is drawn, add the forces. So both masses must have their weights acting on them, and tension. Tension is the same for both objects because the string passes over a smooth pulley. It's sensible to think that the lighter mass will accelerate up and the heavier mass will accelerate down. That's the first 3 steps. The fourth step is to apply F equals ma to each object. So for the 1.5 g weight, if we choose up to be positive, we will have t minus 1.5 g is equal to 1.5 a. And again, if we apply F equals ma to the 5g weight, taking down to be positive because it's accelerating down, we'd have 5g minus t equals 5a. It's minus t here because down is determined to be positive, so the tension which acts up in opposition must be negative. Part A asks, calculate the acceleration of the system and the tension in the string. Well, the 2 equations that we have here and here can be solved simultaneously to find tension and acceleration. By using elimination and adding the 2 equations together, we're left with 3.5 g equals 6.5a. Therefore 3.5 over 6.5 g is equal to a. That's 5.277, or more appropriately 5.28 meters per second squared. We're also asked for the tension. The top equation here is just a bit easier to use. T equals 1.5a plus 1.5g. Therefore T is equal to 22.62 newtons. In part B, calculate the maximum speed of the 1.5 m mass when the 5 m mass hits the floor. At this point we say the 5 m mass is initially 3 meters above the ground, meaning that it has 3 meters to fall through. This is essential for part B. If maximum speed or different speeds are mentioned and a distance is mentioned, essentially 3 meters here, then the problem must relate to subat, so long as acceleration is constant. If we take down to be positive, so it falls 3 meters down, the 5 m mass accelerates at 5.28 meters per second squared. The system is released from rest. We'll calculate the maximum speed, so that would be the speed right before it hits the ground. We're not interested in time, so we need to use the equation that doesn't have time, which would be v squared equals u squared plus 2as. V squared is equal to nothing for u as it's 0, 2as, so 2 times 5.28 multiplied by 3 to 1.66. V is equal to 5.627, 5.63 meters per second. Finally, calculate the maximum vertical displacement of the 1.5 m mass, which is part C. So again, this question is also a SUVAT question. We can tell this because it says the max, it refers to the displacement. And again, this is a constant acceleration situation. So we should put in what we know. So the 1.5 m mass is going to be accelerated up by the tension. Then when the 5 m mass hits the floor, the string goes slack. But the 1.5 m mass still has some speed, it's still travelling up. That's what we want to find. That's the distance that's in addition to 3 meters. So we'd like to know that. We'll say that it starts with 5.63. So we're starting this SUVAT from where the last question left off, with 5.63. The final velocity will be 0 because the 1.5 m mass reaches its maximum height. The acceleration, well, in this case the only force acting on it is its weight, so acceleration is minus 9.8, and here we're taking up to be positive. We don't care about the time taken, and we're not asked, we don't care about it and we're not given it, so just cross that out. Again, we need to use the same equation as last time. V squared equals u squared plus 2as. So 0 was 5.63 squared minus 2 times 9.8 multiplied by s. 5.63 squared is equal to 19.6 times s. Calculate s. S is equal to 1.615 meters. So in addition to being pulled up 3 meters while there's still tension in the string, i.e. while the 5 m mass falls down by 3 meters, it also travels up 1.615 meters. So just go back, calculate the maximum vertical displacement. That's it. So 4.6 meters. That's it.